All right. Hello, everyone. Welcome to today's class. Today we'll talk about statistical foundation. So this part is a bridge that connects the exploratory data analysis and inferential data analysis and prediction. Okay. So we'll talk about, we'll use one example to introduce some concepts in this part. For example, what is a sampling distribution? What is a sample statistic? And how to quantify the uncertainty of sample statistics. So let's start. So the ultimate object in data science is to extract meaningful information from data, right? And the data wrangling and visualization are just tools. Wrangling is used to reorganize observations, clean data, transform data, to prepare data for modeling or visualization purpose. And visualization connects our minds with data to help us finding patterns. So visualization is a very good tool to help us to figure out some patterns. Our human eyes are very good at catching patterns. However, we are also easily misled by accidental patterns that appear in random noise. So we need something else to help us to figure out, to identify if a pattern is a true relationship or is just due to randomness. And statistical methods quantify patterns and their strengths. And so using some models to quantify the patterns, and also use probability theory to sort of assess the validity of the relationship. Okay. So they are essential tools to find patterns that are too complex to be seen visually. So it's very possible if the relationship is kind of weak, then our human eyes may not be able to identify them. And they are also useful to interpret data to do modeling. So this is a data science workflow, roughly speaking. Import data, and then tidy data or clean data, and then transform the data as needed. For example, in this step, we can create new variables using existing variables. We can change units of variables, etc. We can also impute missing values. And then we may visualize the data and then do an initial round of modeling. Okay. Then if you think the model is good, then you can go ahead and communicate it to your customers or your supervisor. If the model is not good enough, and you might go back to transform your data again. Right? So the middle circle might be, you may need a few rounds of this middle circle. Right? So this is a diagram of data science workflow. Right? So before we start, let's take a look at a few concepts. So first, EDA, exploratory data analysis, and CDA, confirmative data analysis. So far, in the first three modules, we focused on EDA. So we use EDA analysis to investigate the data integrity, to see if the data is valid, or is there any problems or issues, any outliers, any problems, potential errors. And then we can use visualization to generate hypotheses. We can also calculate some summary statistics, right, to figure out relationships, right? So for example, smoking is related with cancer. So this kind of hypothesis we can generate from EDA analysis. And in EDA, actually, we may use visualization as well as modeling. as tools in EDA, including modeling, because we can use some simple models to create hypotheses even. And it typically involves many iterations of transform, visualize, and model the middle circle. So this is the EDA. And then the other type is confirmative data analysis. So a few components. So first, we can confirm that the fitting model is appropriate. So we might need to go back and check model assumptions. So there is never ever a correct model, truly correct model. We can only try the best to figure out the best model. But in order to create a model or fit a model, we first need to make some assumptions. Okay? Models always have assumptions. So after we fit the model, we need to go back and check if the assumptions are valid or not. For example, if you fit a linear regression model using the least square method, and before you want to do any inference about the model, you need to go back and check model assumptions. For example, the mean of the error terms should be 0, and there should be you should observe some constant variance among the observations, etc. And next, you can confirm the hypothesis is true or not. In linear regression, you can you can do a t-test for the slopes and to see if the coefficient estimate is significantly different from 0. For example, if it's a simple linear regression, the t-test will be about this. Sorry, should be. Okay. To check the slope is equal to 0 or not, right? To establish linear relationship. So to confirm the hypothesis is true. The hypothesis usually in a linear model is there is a linear relationship between X and Y. And then prediction accuracy and statistical inference. So this part is used to extend your conclusion found in the sample to a larger population. So this is called inference, statistical inference. Okay? Or you may focus on prediction. Right? Usually machine learning models are focusing on prediction, doing prediction. So they don't really care about the relationship between X and Y. The focus is on predict the Y value using some new X values. And then you can also use visualization to graphically convey the conclusion. And lastly, in general, data used in EDA are not used in confirmation. So basically, so you see, they are quite different, but they may use the same tools. Both of them can use visualization and modeling, but they have different purposes, apparently. Statistical methods or methodologies refer to the collective knowledge about the following models, different families of models, and within each family, there are different types of models, and methods to fit the model. We may use some traditional way to fit a model. We may use computational way to find a model. And assumptions and situations under which models can be used. So this goes back to the assumptions. And then methods to quantify the uncertainty in model fit. Remember, we usually only have access to a sample of data, which is not the entire population. So consequently, because the sample is random, whatever model you created using the data is also random. Right? So anything that is random should be anything that is random is uncertain. Right? The coefficients like slopes, intercepts, they are all random. So we need to quantify their uncertainty so that we can make conclusion with a certain precision or confidence. Okay. And last one is quantification of the strength of the evidence. For example, the p-value is usually used to quantify the strength of a hypothesis test. And take a look at this diagram. So this one shows you the relationship between sample data and the population, and also in reality, the data and how to consider data. So the word data is actually from the Latin word for given. So that's why data is assumed to be fixed, usually, a data set. Observations in a data set are assumed to be constant or fixed. However, in the statistical world, we don't actually think the data we have are fixed. Right? They are actually random. So take a look at the first part. Okay? So data are considered as drawn or observed from some unknown mechanism. Some unknown mechanism is used to create data, somehow like this. It may be an experiment. You can use some experiment to generate data, or if it's not possible to do experiment, you can observe some random phenomenon and record the observations. So that is how we generate data. And our model will be based on the data, apparently. And after we feed our model, we want to go back and make conclusion about the unknown mechanism. So this process is called inference. And of course, in order to do this, we have to make some assumptions. And then let's see how, if we make some assumption, we can create an abstract illustration of the process. So the unknown mechanism can be represented as a population, either finite or infinite. It depends on the feature of the mechanism. It might be finite or infinite. And then the data we have can be considered as a random sample drawn from the population. No matter the sample is created using experiment or observational studies. Anyway, it is a random sample for a population. So usually we use capital letters x1, x2, all the way to xn to represent observations in the random sample. I will use capital letter because they are random, essentially. And then we can fit a model and then do inference about the population. So in statistics and also data science, the data we have is considered as a random sample from the population. So in today's lecture, we will examine this concept extensively. So we will use one example. We will still use the NYC Flies 13 package. In particular, we'll only use this data set, the flights data set. Remember, the flights data set contains flights information which departed from New York City in 2013. It is a quite large data set with these many observations. This is the complete population of all the flights departed from NYC. And suppose we want to develop a travel policy for business travelers based in New York City. Imagine that a traveler has a meeting in San Francisco at a specified time T in 2013. And your policy is to make sure that the traveler won't be late for the meeting. So that you want to develop a policy cut so that it defines how much earlier than T an acceptable flight should arrive in order to avoid being late to the meeting. So the purpose is just to find this policy cut. How many minutes ahead of the meeting time that is acceptable to avoid being late. Of course, in practice, in the real world, the arrival time is kind of random, might be very late, might be slightly late, might be maybe even ahead of the arrival time. Right? So we have to develop the policy so that in most of the cases we won't be late, right? But we can tolerate some small chance, like small chance cases. For example, 1% of being late or 2% of being late as possible. So, however, if we actually have the complete population. Okay, we have all of the flights in 2013. So we actually can just look at all of the flights and pick all of the flights that won't be late. Will arrive on time. However, this is not realistic. In practice, if you need to develop a travel policy, that means you don't have access to the whole population of data. You are doing prediction, right? So in order to imitate the scenario, instead of using the whole population, we will only generate a very small sample of flights from NYC to San Francisco and develop our policy using the small sample only. And then because we have the whole population, we will be able to evaluate our policy and study the uncertainty of the policy cut. So this is the whole story. So we first filter out observations that flies with destination equals San Francisco. And we also remove all of the observations with missing value in arrival delay. So this is a variable of interest, of course. And we save all of the flights in SF. So SF is the population of interest, all of the flights departed from New York City to San Francisco. And instead of using this, we generate a random sample with 25 observations from SF and call it sample 25. Notice that we use this function, sample n. So this function can be used to select rows randomly from a data frame. So the argument is size, 25 rows. Save the result here. And we also set the random seed so that each time we run the code, we select exact the same 25 flights. All right, so let's first examine our small sample. We have access to these 25 observations. So we can do whatever we want, right? We can call the summary function and calculate some summary statistics, the 5-number summary and the mean. Right? The mean is 3.32 minutes arrival delay, which is not bad. However, the maximum is 105 minutes, almost 2 hours. If we create a histogram for our small sample of arrival delay, you see it is severely right-skewed. And we see that most of the observations are smaller than 50 minutes. All of them are smaller than 50 minutes, right? But we have some outliers over here, especially this one. This is an outlier, 105. This is the maximum. So this is our sample data. Based on this little sample, what policy can we develop? The very first one is a naive policy, because the longest flight delay is 105 minutes. Let's be very conservative. So our policy is you have to book a flight that is scheduled to arrive at least 105 minutes before. We use the maximum. Maximum is a sample statistic from our sample. We use this. So it's a very extreme policy. So we can do this, take sample and then call the summarize function and calculate the policy cut, which is the maximum of arrival delay. And this is our naive policy, okay? And then how well does this policy work? Remember, we have the entire population. SF is the entire population. We are able to evaluate the performance of our naive policy using our population, right? So we can just do this, take SF and call the summarize function and calculate the mean of arrival delay that is greater than the policy cut, which is 105. I take the mean of it is the proportion of being late, proportion of actually being late using the population. So it turns out that is 3.74%. Right? So this is acceptable, right, for our probably for our policy is somehow acceptable. Is a very small error. Right? However, remember, based on our sample, we have 0% of being late, right? So still it's larger than what we expect to see. It's still acceptable. So this is naive policy. Another policy is less extreme because the data arrival delay is highly right skewed. We might, for example, consider the 98th percentile, which means we can tolerate 2% of being late, but 98% of chance we won't be late. If we use this as a policy cut, probably it will work, right? So let's see this policy. Just let the cut be the 98th percentile. We can use the quantile function to find the 98th percentile, specify the p. Right? And it's equal to 95.4. And naturally, it's smaller than the maximum. Right? So this is the second policy using the 98th percentile. We can tolerate 2% of probability of being late in theory. Right? Then let's evaluate it. If we use the entire population SF and calculate the probability of being late, turns out to be 4.4%. Right? So it's much larger than what we have expected, 2%. So what does this result imply? So this implies that the statistic is random, okay? The statistic is random. So it's not guaranteed that what we observe in a small sample will be sort of replicated in a larger population. Right? The policy cut itself is random. So, and let's see yet another policy, a third policy. The two standard deviation policy. The policy using the two standard deviation rule. So this is actually widely used in practice in every industry, everywhere. So this is because many times the data is normally distributed. For normal distribution, we know that only 2.27% of observations will be greater than mu plus 2 sigma. So that is based on normal assumption. The normal distributions. So this is mu plus 2 sigma, mu minus 2 sigma. So this tail is 2.27%. And also this tail was. And the middle part is about 95%. So this is called two standard deviation rule, which means, it's very unlikely to observe any observation that is beyond the two standard deviation from the mean for normal distributions. So if we apply this rule, then the cutoff point will be mu plus 2 sigma. However, remember, we only have a very small sample of data. We don't have access to mu and sigma for arrival delay. Instead, we should use sample mean and sample standard deviation. We will use x bar plus 3 times s. So we can easily calculate this using the summarize function, calculate the mean and standard deviation, and then cut will be mean plus 2 times standard deviation. So notice that this is a pipe with only one layer, but within the summarize function, the order of execution is from left to right. Right? So mean is created first, and then standard deviation, and then cut is a new variable, but it can call the previous new variables just created. Mean and standard deviation was just created, but it works because it's from left to right in a pipe. So this is the third policy. The policy cut is 83.6. So this is the third policy, book a flight that is scheduled to arrive at least 84 minutes before. Right? Now let's evaluate it. What is the probability that the traveler will be late using this policy? Turns out that is 5.28%. Right? Again, it is more than twice of the expected probability of being late. So this is probably not acceptable. That means our policy it won't work. It's the chance is much higher than we expected. Right? So then let's go back to ask what has gone wrong. To answer this question, we might need to check, was the assumption appropriate? What do we know about uncertainty in estimation of mu and sigma? So first, was the assumption appropriate? Go back. From this histogram, we see that the data is severely right-skewed. Apparently, with so many outliers for such a small sample, the data probably is not normal at all. So the assumption is indeed invalid. We should not use the two-standard deviation rule at all. That's why it performs poorly. And also, the uncertainty of the estimation of mu and sigma, we can study it now, right, from now on. So let's try to quantify the uncertainty. How to quantify uncertainty of sample statistic? The answer is we use sample distribution. We either simulate the sample distribution or if it's possible, we derive the sample distribution. So how reliable is a sample statistic? So from our experiment, the sample standard deviation is 40.1. The population standard deviation is 47.7. So our sample standard deviation is smaller. And the sample mean is close to the population mean. It's close to the population mean. However, what if we draw a new sample of the same size? And let's calculate the mean and standard deviation and see what will happen. So let's change the C to 99 now, right? And then draw a sample with size 25. So this will be a new sample with 25 observations. And the mean is negative 1.72, and standard deviation is 30.2. So apparently the mean changes a lot, right? From positive to negative, and standard deviation shrinks from 40.1 to 30.2. So all of these sample statistics are quite random, right? They are quite variable, right? And so now let's go back to our population and evaluate our policy by repeatedly drawing samples with the same sample size from the population. And let's try to establish a sampling distribution for sample mean using simulation. Of course, we know that in statistics, it's very easy to figure out the sampling distribution of sample mean theoretically. Right? But now let's use simulation to establish it. Right? We first create an empty list called trials and set the seed go back to 100. And we use a for loop to draw random samples of the same size repeatedly, and at the same time calculate the mean and standard deviation. Right? So see, in each iteration, we take SF, sample 25 rows randomly, and then calculate the mean arrival delay and standard deviation of arrival delay, and save the result in the ith component of the empty list trials. So in each iteration, we'll fill the trials list with 2 rows. So the trials is somehow like this. If you use a matrix to denote it, it will have 100 rows and 2 columns. The first column is mean, and the second is standard deviation. In each iteration will fill 2 numbers. And after the for loop, trials, remember, is still a list. A list is not exactly a data frame. It doesn't look like this, like a table. It's a one-dimensional object. In order to make it like a matrix, we can use the bind rows function to unlist the list. Okay. And then at the same time, we will add a new variable, policy.cut, which is mean plus 2 times standard deviation. Call it trials df. So trials df will have a third column, which is cut, policy cut. So this is this table, trials df. Then we have a sample distribution with 100 observation. And alternatively, we can use the apply function. We have learned this function before, right? This family before. The replicate function can be used to repeat one function multiple times. So we repeat the sample function 100 times and save the result in samples. Remember, the replicate function will return a list. And then we can apply the sapply function on the result, which is samples. This is a list, and calculate the mean for each component of the list. Remember, the sapply function will take the list and return a vector, not a data frame. So this is an alternative way to generate this sampling distribution of policy cut. So take a look at the first 10 rows of trials DF, 3 columns, mean, standard deviation, policy cut. Of course, this one is of interest only. And we can see that the policy cut actually vary a lot. You see, the smallest is 65.6, but the largest is 163. So it's very variable, very variable. And we can calculate some summary statistics for the last column. So these are all the policy cuts. The minimum is 28.4 minutes. Maximum is 202 minutes. And the mean of policy cut is 94.7, and standard deviation is 37.6. It's a very big standard deviation compared to the mean. And we can also create a histogram for our sample distribution of policy cut. So apparently it's still right-skewed. It's quite right-skewed. From this simulation analysis, we see that we were lucky in the first sample of sample 25, which provides only 5.3% chance of being late. This could be more than 14.6%, if we use, for example, 29 as the policy cut, or the probability can be less than 1% with a 203-minute policy cut. So from this study, we know that the two standard deviation rule, a policy cut is very variable. It's very variable, and it might not be very reliable. And some other issues made that we need to consider. First, is normal distribution assumed for the population appropriate? So apparently not. Are there any outliers? Yes, we have outliers. And next, conditioning. Should the policy depend on airlines, the time of year, day of week, and time of day? Yes, these factors all affect arrival delay, the variable. But in order to consider all of these factors, we need to construct a model which will consider all of these factors. But for now, we haven't used any other variables yet. We focus on the variable of interest, which is arrival delay only. And also lastly, any missing values. So that's all about this small session. The main purpose is to differentiate sample data and the population. And also whatever conclusion made based on the sample is random. There is uncertainty in it. We studied the uncertainty of a random quantity, which is the sample mean. We essentially create a sample distribution using simulation. And we have observed a big uncertainty in the distribution of sample mean. And the next small session is about sampling and Bootstrap. So this is also a very important topic, especially in data science, because most of the data science, machine learning models and the data science strategies are data-driven and heavily rely on computation, simulation. And Bootstrap is a very important strategy in many aspects in data science and machine learning. In model tuning, in model assessment, a lot of areas. So let's take a look at this session by sampling and Bootstrap. So let's go back to our example. We draw a sample of 25 rows from SF, and we try to develop a travel policy, a policy cut, so that the traveler won't be late for a meeting. At this time, we will simply focus on the mean arrival delay. I suppose we just call it X bar. So this sample statistic only. We want to study the distribution or the features of sample mean in this small session. So first, the mean of arrival delay in the smaller sample is 3.32. So this is called a sample mean, which is a type of statistic. A statistic is any quantity that is calculated from a random sample. All right. So let's study the reliability of sample statistics. So how reliable is this statistic? To answer this, we can see how much the statistic will vary from a sample to another. Because we have the population, we can draw many different samples from the population, each with the same size, and calculate the sample statistic on each of those samples. Of course, we have done this before, but now, remember, our focus is on sample mean. It's not a policy cut anymore. We just focus on sample mean. So we do almost the same thing, except for we use more iterations. We will generate a sample of size 25, 500 times from the population, from SF. And in each iteration, we generate the sample and then immediately calculate the sample mean of arrival delay and save the result. And then we unlist the trials list, and then we calculate some summary statistics. Notice that this function, favorite stats function, can be used to summarize data very well. I think this function is built in Mosaic, this package. So it will calculate the 5-number summary and the mean and standard deviation, number of observations, and number of missing values. But it's a pretty good function to summarize some numerical variable. So if the data is very it's kind of symmetric, you can use this group of statistics to summarize your data. If your data is very skewed, you can consider using this group of summary statistics. And also you can see how many missing values. All right, notice that in the sample n function, I specifies that replace equals false. This means in the sampling process, I will not allow repetitions in the rows. If a row has been drawn from the population, then this row will not be drawn twice the second time. So there is no repetition in the sample. Because we have a very big population and our sample size is small, replacement with replacement is not necessary. And we don't want to have repeated observations. This is actually the default option for sample n. But I still put it here because later on we'll compare this argument for the Bootstrap process, in the Bootstrap process. All right, now let's create a histogram for this sample distribution of sample means. Okay. So let's review the definition. A sample distribution is the distribution of the sample statistic from all potential samples of the same size from the population. Okay, so this is the definition of a sample distribution. And so in our case, there are zillions of potential samples, of course. And so it's impossible to consider all of the samples and then calculate the sample mean and create this. Instead, we approximated it using 500 trials here, which is big enough usually. 500, even 100 should be big enough because we do it in a random way. So the sample is a good representation of the entire sample distribution, all of the potential samples. Okay, 500. And the shape of the sample distribution is worth noting. It's a little bit right-skewed, but it's still centered at around 3.04, which is close to the truth. But let's compare the mean of means and the true population mean. So now let's sort of review the features of sample distribution of sample mean. So let's review it. Sample mean by definition is this. Suppose we have n observations, then the mean of sample mean should be equal to the population mean. And the standard deviation of sample mean should be equal to the population standard deviation divided by square root of n. N is the sample size. So now let's see, the first number is the mean of sample mean, right? Mean of sample mean, 3.04. Right? And remember, we have the population. The population's mean is 2.67, very close. Right? Not equal because we only drawn 500 samples, potential samples. If we do it in an exclusive way, like consider all of the samples, then calculate the mean, they should be equal, exactly equal. Okay. And standard deviation, the standard deviation of the sample mean is 8.77 something, right? And the standard deviation of the population is 47 something. Okay. So notice that if you divide this by square root of 25, which is 5, you'll get almost the same number as that one. Right? So the features of, so we verify the features of sample and distribution of sample mean. Right? All right. So remember, we want to measure the reliability of a sample statistic, right? So we usually consider a few aspects. First, the mean of the statistic. Better if it is close to the truth. For sample mean, it's a very good statistic because we know that the mu of sample mean is equal to the mu of population mean, exactly equal. And secondly, the standard error of the statistic, better if it is small. We hope that sigma is small, but and also constant interval can be used to quantify the uncertainty or reliability. With a certain level of confidence, for example, 95%, we hope the confidence interval to be very narrow, which means very precise. You can estimate the population parameter very precisely. All right, in the above example, the mean of sample mean is close to the population mean, and the standard error is a little bit too large to be acceptable, especially compared with the sample mean, mean of sample mean. And we can also calculate the 95% interval for the population mean using this formula, x bar plus or minus 2 times standard error of x bar. This is an approximate 95% reasonable for sample mean. All right, so then let's study some more features about sample distribution of sample mean. If we increase the sample size, the standard error will decrease. Remember, I have shown you the formula. And the standard deviation of sample mean is equal to sigma divided by sigma of n. So there is a negative relationship between n and sigma of x bar. The larger the sample size, the smaller the standard error. Right. So let's use a round of simulation to verify this result. Right. So we will use a nested for loop to complete this task. First, create an empty list called trials.all. Then create a vector with the 4 sample sizes we will consider: 25, 550, 400, and 200. The 4 sample sizes. And then a nested for loop. The outer loop is about different sample sizes. And so in each iteration, we consider 1 sample size. Right? And in the outer loop, we create an empty list, call it trials and then record the sample size, right? And then in the inner loop, we generate a random sample from the population, okay? And immediately calculate the mean arrival delay and also keep record of the sample size in that iteration and save it in here. Right. So after the inner loop is done, we will have 500 observations. Right? We will have a list of 500 components, and each component has 2 elements: the sample size and the sample mean. Right? So for each sample size, we do the same thing. And finally, we unlist the trials. And so the data frame created here, the list created here, and the save it as the J's component of trials all. So this one is the biggest list, which has 4 components corresponding to the 4 sample sizes. Anyway, trials.all is a list, and then we unlist it to make it a matrix. So dimension of the overall matrix is 2000 by 2. Basically, we have 500 rows for each sample size, 500 for each. And each one only has 2 columns, which is the mean, the n and the mean. Okay. You have to keep record of this n because later on we want to compare the summary statistics for different sample sizes and different n values. Take a look at the first 3 rows of trials.all. You see 2 columns, sample mean and n. All right. So then we are able to compare the sample distribution of sample mean for different sizes. So notice that we create a histogram for each sample size. First is 25, still right skewed. This is because, remember, arrival delay is a right skewed random variable. Originally, it was very right skewed. With a small sample size, 25, relatively small sample size, the distribution of X bar is right skewed. And when sample size increases to 50, it's almost symmetric. Right? You can see the bell shape already. And with 100, it's also approximately symmetric. And lastly, 200, more symmetric, and more bell shape. So this simulation demonstrates 2 fundamental results in statistics. First, the law of large numbers. The law of large numbers says that for a large sample size, and the sample mean is close to the population mean. So the sample mean is approaching the true population mean, which means the sample mean will be in a very small neighborhood of the true population mean. So this is the essence of the law of large numbers. And second is the central limit theorem. So this theorem tells us that for a large sample size n, the sample distribution of sample mean is approximately normal. So no matter what distribution x follows, individual observations follows, the sample mean is approximately normal for large n, for large sample size. Essentially, the rule of thumb is when n is greater than or equal to 30, the distribution is approximately normal for any distribution, right? See the value. And it's more and more symmetric about the mean. So this is the summer distribution, and this slides we verify sorry, we verify the property I just mentioned about the standard deviation of sample mean for different sizes. So the standard deviation of the population is 47.67, right? And we can use this formula to calculate the theoretical standard deviation for different sample sizes. So for n is equal to 25, the theoretical standard deviation of sample mean is 9.54. And our simulation yielded 10.2, which is close. And for 50, the theoretical standard deviation should be 6.75. And we got 6.51, which is also very close. So So we have used simulation to verify that this formula is true. Use computation to verify that. All right. So far, we assume that we have access to the entire population, and we can study the distribution of a random quantity like X bar using the entire population by drawing samples randomly and repeatedly from the population again, in this case, SF, right? However, in the real world, in practice, we never ever have access to the entire population. So in this case, how can we quantify the uncertainty of a sample statistic, for example, X bar? If we only have 25 observations, how to quantify the uncertainty of this? The answer is Bootstrap. So the Bootstrap is a method that allows us to approximate the sampling distribution even without access to the population. The strategy is very simple. We treat the sample as if it was the population. We treat the sample as the population. So in our case, sample 25 is our population. And then we draw many new samples from the original sample. We draw a sample with 25 observations from sample 25. Of course, in this case, in order to make sure that the new sample and the original sample are different, we have to allow replacement, repetitions. So if we do this, we are doing a bootstrap. We're doing bootstrap. So drawing a sample from an existing sample in general is called resampling. And if we let the sample size to be equal to the original sample and allow repetition at the same time, it is usually called bootstrap. So let's see one example. So now, instead of using the entire population SF, let's draw a sample of the same size, like 25, and is a number of rows of sample 25, which is just 25. We draw 25 observations from sample 25. Right? Notice that now replace equals true, so we allow repetitions now. Right? And then immediately we calculate the sample mean of arrival delay, right, and save it in the list. Okay, we keep record of the sample size still, right, and save the result. We call it bootstrap boot df. So this is bootstrap, very similar to just sampling randomly. Right? The only difference is replace equals true now. Right? And also another difference is the sample size is equal to the population size now. Right? From 25, we draw 25. Right? We have to allow repetitions. So remember we did it 500 times. So we have a sample of sample means, right? 500 sample means. And we can create a histogram to observe the distribution of X bar. So you see that it is similar to the one that we got using the repeated sampling from the population. Right? Kind of similar, like also bell-shaped. Yeah. But because we draw these samples from a sample, this is called a bootstrap distribution instead of a sampling distribution. Right? So a bootstrap distribution actually is very similar to a sampling distribution in many aspects. For example, the behavior of the mean, standard error. For example, let's calculate the standard error, standard deviation of the sample mean from the bootstrap sample is 7.88. Right? Previously, we got something like 8 point something, right? So slightly smaller. But in terms of magnitude, they are very close. We can also consider different sample sizes in Bootstrap for comparison purpose. We want to remember our goal is to quantify the uncertainty of some sample statistic with only a small sample. And in order to quantify it, we have to demonstrate that the bootstrap distribution is similar to a sample distribution in almost all aspects. So that's why we will do this simulation, which considers 4 different sample sizes, the same sample sizes that we use for the sample distribution. Right? We do almost the same thing and calculate the standard error of the bootstrap sample, right? 12, 7.27, 3.61, and 3.06. Right? And we can compare it with the standard deviation for the sample distributions with different sample sizes. So see for 25, the sampling distribution has standard error 9.44, and Bootstrap has 12, slightly larger. But for 50, it's slightly larger too. For 100, smaller, and for 200, smaller. So in general, they are close. They are close. So from this simulation, we'll see that Bootstrap is a very good tool to evaluate or to quantify the uncertainty of some sample statistic. Actually, sample means are easy. Sample means is the easiest sample statistic that we actually know everything about the sample distribution of sample mean. We even can calculate the theoretical mean and standard deviation of sample mean, right? We verify that. However, many times the statistic is very difficult. It's very complex, so that we don't have a formula, or the formula is very complicated, right, for the sample distribution of the statistic. For example, standard error is already a standard deviation of sample mean. Standard deviation of a random sample is already kind of not very simple anymore. And also in regression analysis, for example, the model is a linear regression model. Right? For example, you fit a linear regression model using some data, a sample data set, right? And you want to study the quantified uncertainty of the slope, beta 1 hat. Of course, you can do a t-test. It's very easy, and it is in the standard output of the LM function. However, remember, the assumption is the error term is approximately normal. Okay, and this is a very strict condition, actually. In practice, many times the errors are not normal, namely y is not normal. In that case, you should not use the t-test result to do inference about its slope. But using Bootstrap is very simple. We can just draw Bootstrap samples from our data set, both X and Y, basically resampling with replacement. And we fit a model, a linear regression model, using each Bootstrap sample. And then calculate the slope and intercept. Suppose we do it 1,000 times, then we will have 1,000 values of this beta 1 hat, right? It's kind of like a sample of it, right? So this is kind of like it's a bootstrap distribution of beta 1 hat, right? And then we can use it to quantify the uncertainty. For example, you can calculate the standard deviation of beta 1 hat. You can create a 95% confidence interval for beta 1 hat. You can also use the interval to do inference, right, to check if beta 1 hat is if beta 1 is equal to 0 or not. Right? Just check if the interval covers 0 or not. Okay. So it's very convenient to use Bootstrap to do inference, right? Without making any assumptions. Remember, we didn't make any assumption. It's just purely relying on computation, simulation, right? No assumption. Then go back to our travel policy again. So now let's consider another factor, which is months. So we will use Bootstrap to develop a travel policy for each month. Right? And also at the same time, we not only will calculate the policy cut for each month, we will quantify the uncertainty of the policy cut, and also eventually we'll use the entire population to evaluate the performance of this model, of this policy. So we first still create SF, and then, so now we will draw 100 observations from each month. Notice that group data by month, and then generate or select 100 rows randomly from each group, namely each month, and save the result in sample.month. So this one should have 100 times 12, which is 1200 observations. Okay, so 2 columns, month and arrival delay. So this is our sample data. And now we will use Bootstrap to calculate the policy cut. We will calculate the mean and standard deviation of the policy cut also. Suppose we use 95% as 95 percentile as the policy cut, because we know arrival delay is right scaled. And suppose we allow 5% of chance of being late, 5% chance of being late. So let's take a look. We first create an empty list, okay? And then in each iteration, we create we generate a Bootstrap sample for each month, 100 observations, and save it here. And this is a Bootstrap sample of the same size, which is 1200 observations. And then we will calculate the 95th percentile of arrival delay for each month and save it here. Okay. So after this iteration, this loop, we will have 1000 P95s for each month. So totally 12 times. So 12,000 rows in this table. Okay. And then we can summarize the result. Okay. We can calculate the mean and the standard deviation. So this small table contains the policy cut and the standard deviation of the policy cut, the mean policy cut and standard deviation. So you can take a look at. So the last column is used to quantify the uncertainty, and the second column is the mean policy cut. Okay. And we can also create a box plot to compare the policy cut. So namely, you see in June and July, the policy cut has the largest spread or variation. But in February, smaller. So this is the result of the simulation. And lastly, we can use our population to evaluate the policy cut. Namely, we calculate the probability of being late using this policy. So we will just assume that we use the mean policy cut as the policy cut as the policy. Okay, so do this. Select months and arrival delay, and the left join was mean cut by months. Now we do a left join. Basically, we add two columns of constants. One column, month is repeated, the same column. And then we add a new variable called is.late, which is a column of true or false values. If the arrival delay is greater than mean cut month, then it returns true, otherwise false. And then calculate the mean of is.late, which is the probability of being late. So then you see this is the result. So basically, in some months, the performance is not very good. Like for example, in February, March, not really good. And in some months, it's better. All right. That's all for today.